Okay, so the problem we're looking at today is a follow-up problem on a previous problem in this same section. And so there's one piece of information that we need that is missing, and that's that the elevator is coming from the first floor. So I'm just going to add that here, and then I'll talk more about the problem. So we'll say elevator starts on first floor. Okay. All right, so we have this elevator, and it is moving up because it's going from the first to the 34th floor. As it's approaching its destination, it's slowing down at a rate of 2.8 meters per second squared. And then we're asked a number of questions. What is the tension in a few objects and so on. So let's draw a picture here that refers to the situation. Okay. So we've got our elevator. Okay. It's obviously being pulled up by some sort of cord. Okay. Inside, there's a person. Okay. That's going to be one of our free bodies. That person is holding a strap. All right, so we'll put the strap right there. Okay, that's something that we're going to take a look at. And at the bottom of that strap is a bag. Okay, so those are the objects that we are interested in. All right, we'll go ahead and label those. All right, so person, strap, and bag. All right, and this is the elevator itself. Okay, so we have some velocity. All right, so, and we'll define the positive y direction as up. All right, so plus y will point up this way. We have an initial velocity that also points up. All right, so that is v naught. We have gravity acting on the system, pointing downwards. Okay, so this will be our gravity. All right, so, all right, here is g equal to 9.8. All right, negative 9.8 meters per second squared as a vector. All right, like so. And then we've got the acceleration as well. Now here's the question. What direction is the acceleration pointing? Well, since the elevator is moving up but slowing down, that means that the acceleration that's slowing it down from its initial velocity must be downwards. So then we also have that the acceleration a is negative 2.8. Okay, so let's take a look at the first part of the problem, part A. All right, so we're going to start in part A. It asks for what is the tension on the held bag strap. Okay, so to answer that question, let's look at the forces on the bag. So forces on the bag, and we'll quickly see why it's good to focus on the bag to answer a question about the strap. So we've got the net forces acting on the bag is going to be the tension force acting up on the bag and gravity acting down on the bag. And that's going to be equal to the mass of the bag times its acceleration, because the bag is not at rest. It's accelerating. So I'm going to call that A. Notice I'm just leaving A as a scalar. That's the same A that's represented as a vector over here. Okay. So then what we're going to do, okay, and then, yep, the gravitational force points downwards. Okay, so then we're going to go ahead and solve for the tension force. So then the tension force is just going to be the gravitational force plus the mass of the bag times acceleration. Okay, now let's plug in some values here, because we have here m times 9.8 meters per second squared. Okay, and then and we are given the mass of the bag in the previous part of the problem, so it ends up it's 12 kilograms. Okay, that is known information, so I'll put that over here, that the mass of the bag is known to be 12 kilograms. Okay, and I've already taken into account the negative on acceleration because I had the vector pointing down. However, I just naively plugged in any old acceleration as a scalar, and so then we want to take into account that it's negative. So we'll put that here parenthetically, that we have negative 2.8 meters per second squared. And of course that makes sense, because as you accelerate downwards, the tension on the strap in the bag is going to become less and less. You can even think in the extreme case, if this elevator was slowing down much slower than you'd want, or at a much greater rate than you'd want an elevator to slow down, then you'd actually feel a moment of weightlessness where the tension would be 0. And that'd be if the elevator was decelerating at 9.8. But let's actually find our tension here. That is a non-zero tension. And what we get is 84 newtons. Okay? And that's just by taking 12 kilograms times 9.8, and then, all right, and then subtracting out the 12 times 2.8. Okay? And, you know, of course we could have actually factored out 12. That would have been better, but we'll do 2.8 here. And we get 84 newtons. Okay? So that's part A. So moving on to part B, put down here. We want to look at the strap. Okay, so forces on the strap. Okay, so we have F net on the strap is going to be the force of tension acting on the top of the strap minus the force of tension acting on the bottom of the strap equal to the mass of the strap, times the acceleration. I said uh-oh because, well, the thing about straps is unless explicitly stated otherwise, we do assume they're massless. So here we have 0, which means that F net is also going to be 0. Because if you have no inertia, then you can have no force. Okay? And that's 0 newtons. All right. So a somewhat trivial part, but crucial for understanding things. All right, and so I do want to actually go ahead and add some forces on here, the ones that I'm referring to. This would be the Fg on the bag. Here's the tension that I referred to a minute ago. There's another tension acting down. They're equal in magnitude and opposite in direction. Then we also have the normal force pushing up from the floor of the elevator. And then we have the gravitational force of the person on the floor of the elevator. Okay? And we'll get to that in just a minute. All right. Okay, so let's take a look at part C. All right, so part C, we're asked about the normal force exerted by the floor of the elevator on the person's feet. Okay, so let's go ahead and look at that. So on the person. So what do we have? We'll look at F net again. Okay, we're going to have the normal force pointing up, the gravitational force pointing down, and since the tension is also acting on the person, we also have the tension acting down. Because we can see, right, if I drew the one I drew in here, right, the messiest of my T's, but here I can redraw it, is the tension force that is acting on the person. So treating the person as a free body diagram, there are 3 forces acting on them. Okay, 2 downward forces and 1 upward force. All right. So then we'll go ahead and set that equal to the mass of the person times the acceleration. Okay. All right. So then we want to solve for the normal force. Okay. So when we move on to do that, the normal force is going to be equal to the tension force plus the gravitational force plus the mass of the person times A, which will be negative, as we will soon see. And so what this is going to look like, the normal force is going to equal the 84 newtons that we solved for previously, and then plus 70 kilograms, which is the stated mass of the person. Okay. 70 kilograms. And then times gravity, 9.8 meters per second squared. And as before, minus 2.8. And that's simply because we're plugging in the negative there for its scalar value. Meters per second squared. Okay. So let's enter this in the calculator. We'll just take the value from above and subtract, or rather add. And then we're going to add the weight, so, or rather the mass, 70. And then 9.8 minus 2.8. All right. And I get 574 newtons as the value of the normal force, which is less than we'd get if the elevator wasn't slowing down. Okay? But of course, it's only less because the elevator is slowing down as it was moving upwards. If it was slowing down when it was previously moving downwards, then everything would be heavier. The tension would be greater, the normal force would be greater, because you'd be pushed into the floor by your inertia. Okay, so in part D, it asks about a free fall case. It says, if the elevator suddenly succumbed to catastrophic mechanical failure, and you, the bag, and the elevator were all in free fall, what would be the answers to the previous parts, A, B, and C? Well, if the elevator was in free fall, then A would equal G, okay? And I mean here that they'd also equal each other in sign, right? Because they would both point downwards. So they'd both be negative 9.8, okay? So then we could go on to say that we'd have a tension force of 0, and the normal force would just be the tension force plus the mass of the person times G minus G, which of course would also just be 0. Okay, so all the forces, the tension force and the normal force, would both be 0. Everything would be 0. Okay, 0 newtons here and 0 newtons here as well. Okay, and that's because in a free fall situation, that's really weightlessness, and we'll show that later that that is also true of astronauts in orbit. They are weightless because they are in free fall, not weightless because they are outside of the effects of Earth's gravitational field. All right, thank you.